Triglycerols are hydrolyzable lipids, which means that they're lipids that can be broken down into smaller pieces in a hydrolysis reaction. So hydrolysis reaction. And maybe a more general way of looking at this reaction is as an ester hydrolysis, because really what's being broken down in here are the individual ester bonds. You see, this is an ester. This carbon is double bonded to an oxygen and then bonded to an additional OR group as well here. This would be an ester. And this, when we break these triglycerols down, this bond right here and right here and right here, these are the bonds that we're breaking. So this is actually more generally an ester hydrolysis reaction. Now this reaction can occur in the presence of either an acid or a base, but I want to concentrate on the base-promoted ester hydrolysis because it has some specific implications for these triglycerols that we've been talking about that I want to build towards. So the base-promoted ester hydrolysis. So to give us a head start on this base-promoted ester hydrolysis, I went ahead and I kind of drew us in a backbone here for this reaction mechanism, and I'll just try to go ahead and walk us all the way through it. So starting off, what we have is an OH group right here, an OH group. This is going to be our base. It comes in and it nucleophilically attacks this carbon. So this is a nucleophilic addition reaction, and when these electrons come here, it forces the electrons, some of the electrons from the carbon-oxygen double bond to kick up to the oxygen, which the oxygen pretty readily accepts these electrons. It's pretty electronegative as an atom. So in this tetrahedral intermediate, we end up with an anion, of this oxygen. And this is our carboanion tetrahedral intermediate, but these electrons end up coming back down to reform this carbon-oxygen double bond because the double bond is a little bit more stable, and it forces these electrons from this OR group to push out, and this OR group becomes a leaving group. So this would be step 1. We kind of have the addition of this OR group, and in step 2 here we have the OR group, which is now got an extra pair of electrons, leaves. So you can see in this step our OR group, which would be negatively charged, has left, and what happens is this OR group now is a really strong base. It's got this extra pair of electrons. It was a good leaving group, but it's a strong base, and we've formed a carboxylic acid. You see here we've got a carbon double bonded to an oxygen and then with an OH group, and this is a strong acid. So that would be the second step. In this third step, we have an acid-base proton transfer. So this OR group, this strong base, is going to pick up this proton, and these electrons are going to move back onto this pretty electronegative oxygen, which was willing to give up this hydrogen because it's such a strong acid, and you end up with a product of a carboxylate anion. So we've got that negative charge, and then our alcohol. So this would be the base-promoted ester hydrolysis reaction, and you can see that this is the bond that we're breaking. We've broken that bond right here. Now in our body, this base-promoted ester hydrolysis that allows us to break up these triglycerols is the starting point for all of our fat metabolism reactions. So if we want to take a fat and metabolize it and break it down so that we can get the energy out of it, remember that we had 9 kilocalories of energy. If we want to metabolize fats, I'm going to write that up here as one of the uses of this base-promoted ester hydrolysis reaction. We're going to start with this mechanism right here. So in the cells of our body, we're able to use specific enzymes called lipases, lipases to facilitate this reaction so that we can break down fats and eventually get energy out of them. And that reaction is hugely significant in our bodies, but another application for this reaction is actually in the creation of soaps. So soaps, and what happens is when you use a strong base like NaOH, so maybe like NaOH, which is sodium hydroxide, as this base promotion, you end up with a sodium cation at the beginning of this relationship. That's where this hydroxyl base group comes from the sodium hydroxide, and you end up with this sodium cation that just kind of floats through this reaction unused until the very end, because what you have is a cation here and an anion. This is a polyatomic anion, this carboxylate anion, and it links up with the sodium cation to form an ionic salt. This is an ionic bond, so we've got a salt here. Now, if the carboxylate anion in the salt that you just formed happens to be from a fatty acid, which is the case in this triglycerol, remember these are three fatty acids, then you have a really neat property in the product, because this R group right here is actually a really long tail. Remember with the fatty acid tails, I'll just go ahead and draw a whole fatty acid here. So this might be an example of the carboxylate anion with the fatty acid. You have this really long carbon tail, and then you have this sodium cation that comes in. If this is the salt product, which again is the case with the triglycerol, then you have a long nonpolar section here for the tail. So nonpolar with a really polar head in this ionic bond. And this allows this salt, which is a soap, to dissolve both nonpolar molecules and polar molecules. So the nonpolar side is going to wash away. It's going to dissolve things like grease and oil. And then the polar side is going to allow this mixture to wash away with water, because the polar side can dissolve in with water. And this is exactly what allows you to take the grease, which gets all over your hand when you're working, say, on a car or on a bike, and wash it away with soap, with heavy soap. So this soap actually kind of lends towards the reaction name for a base-promoted ester hydrolysis, which is saponification. Kind of a long word, but saponification. This is exactly what saponification is referring to, the base-promoted ester hydrolysis reaction.